Hi everyone. We are a team of three members: Sonak Mandal, myself Shanmukh Sanath, and Dhanush Kumar. So, for this knowledge modeling and semantic web technologies course project, we have worked on graph embeddings, where we try to create and evaluate the embeddings for knowledge graph. And coming to introduction. So, these knowledge graph embeddings are a set of techniques where we try to represent the entities and the relationship between those entities in form of a feature vector. And these feature vectors capture the semantic meaning of entities and the relationships. So in a latent space of these feature vectors, we can see similar entities and relationships represented vectors or feature vectors are close together as opposite to the dissimilar entities. And these embeddings have a wide range of applications where they can be used for link prediction, entity classification, and these are mainly used in recommendation systems in daily life. And also they have been particularly very helpful in natural language processing field, where they have been used to learn representations of words and phrases that capture their semantic relationships. Coming to problem statement, traditional methods of knowledge graph uh, have very difficulty in reasoning and inference, and these are not scalable to deploy in the daily life applications. So to overcome these limitations, we tried to convert this knowledge graph into an embeddings of feature vectors, which are very easy to use and can be easier to deploy. So the main objective is to implement and evaluate state-of-the-art knowledge graph embedding techniques, such as transient RDF to vec. So the goal is to compare the performance of these methods on a link prediction task. So we particularly focused on the link prediction task. And we have used the standard British Geological Survey dataset. So this is published by British Geological Survey in United Kingdom, where they have published the geology maps in different formats, such as GeoIndex, linked data triplets, and ArcGIS Atlas. So we use the linked data triplet data format, where they shared files of format NT, nothing but N triples, which has head, label, and the tail format. And these are the following files that are present. First one is geochronology, which has several geological timescales in that file, details in that file. And second one is earth material class, which has different types of earth material and other substances that are being recorded by BGS. And other one is lexicon. This lexicon has details of rock units and other terms that are present in the BGS maps. And finally, 625K geology map, which has a generalized digital geological map in form of triplets. And coming to methodology, so the basic approach involves converting the graph nodes and the relationships into an embeddings, and then taking the each triplet, that is head, the label, and the tail. Label is nothing but the relationship between head and tail as one data point. And coming to getting node embeddings, so we implemented two models, Transy and RDF to vec. I'll be explaining Transy model, and RDF to vec will be explained by Sonak. So Transy model relates to translations in embeddings of the node. So for each directed edge in the graph, that is combined head, label, and the tail relationship or the triplet, we try to generate the vectors for each of these head and label and the tail separately. And the basic task or the basic reasoning is that the summation of head embedding along with the relation embedding is close to the embedding of the tail. This is the main reasoning they have used, and based on this idea, they have tried to create embeddings. And I'll explain more from the code. So this is the Transy model. This is nothing but a basic machine learning model where we initialize the embeddings for entities. Entities is nothing but the head and tail, all the entities. And the relationship is nothing but the label I have explained before. So we create embeddings for these two. We initialize the embeddings randomly, and then we have a training loop. In training loop, so basically the triplets are two types. One is the positive triplet, other one is the negative triplet. Positive triplet is nothing but the label bit the label, which is the relationship between head and tail, is it's the true. I mean, they have the relationship between head and tail. And for negative triplets, the label given is not the true relationship between head and tail. So it is kind of triplet loss training, or we can say they have used the triplet based loss. So here we're calculating. So this score is nothing but the Euclidean distance. The Euclidean distance between head embedding plus relationship embedding and the tail embedding. So they have calculated score for positive triplets, negative triplets, and we tried to minimize the score. And also we have a margin. We have set up a margin so that positives are very close and the negatives are very far apart. And we have a training loop to train all the triplets that are being obtained from the BGS dataset. And the details of data extraction is will be explaining by Sonu. That's it. Next, Sonak will be explaining about the this RDF2Vec and other methods. Thank you.
Hi, my name is Shaunak Mondal and I will be talking about the RDF2Vec model, which is a type of graph embedding model that can be used for knowledge-based graphs. Now discuss the motivations for using such a model. It has already been recognized that the linked open data is a valuable source of extra information that can be used to augment our current databases. It is a known fact that such augmentations improve the performance of the model at hand. So this work attempts to use language-based modeling approaches for embedding these graphs so that they can be used by these models. We note that the generation of embeddings and the dataset and tasks and the model used are all independent factors that can be taken into account separately. We can generate the embeddings using the method presented in this paper, and we can then independently use any model and dataset that has the same embeddings. We now discuss the details of the algorithm. The algorithm is divided into two parts. The first part converts the graph into sequences, and the second part converts the sequence into embeddings. The first part of the algorithm, which converts the graph into sequence, is done using an algorithm called graph walk. In this case, we simply perform BFS search on each and every node of the graph up to a certain depth as specified by the user, which is an hyperparameter. We return all the paths that is traversed by the BFS algorithm as sequences. A point to be noted is that if we encounter any literal on the path, then we discard the literal as well as the relationship that holds the literal to the previous node, because we are only interested in embedding the nodes and not the literals. The second part of the algorithm converts the sequence into embeddings. This is done using an NLP-based technique called word-to-vec. Here, the first variety, called the continuous bag of words, is depicted. In this case, the sequence is chopped off into fixed length windows, which is a hyperparameter of the model. The model takes in input the window and tries to predict the central word of the window. Here, WT is the central word and WT minus C to WT plus C is the context. A point to be noted is that the context is not the input but the output, and for all the vectors associated with the inputs are concatenated together as the final input to the model. The probability is taken as simply a softmax function over the dot product of the embedding of the input and the embedding of the output. Training the model will allow us to get the embeddings together with the embeddings of the input as well as output. The other model for converting sequences to embeddings is the skipgram model, which which does just opposite to the bag of words model. Here, given the central word, we try to predict the context words in the window. We can see that the probability that we are trying to maximize is the joint probability of the words in the context given the central words. We assume a simple factoring of the joint probability distribution, and the individual probabilities are modeled again as the softmax function over the dot product of the embeddings. Again, maximizing the probability using the model will finally allow us to get the embeddings which are the model weights. Presentation of the CBOW and the skipgram architecture, which clearly shows the inputs and the outputs. The inputs for the CBOW architecture are actually concatenation of all the embedding vectors, and for the skipgram model, we output a probability distribution for each of the possible outputs. Now we move over to the code walkthrough of the RTF to wake model. First, we have introduced the RTF to leap package in order to deal with the n triples part of the BGS dataset. We created a class where we have extracted the triples and all the entity relations from the triples. We have also discarded any relation in which the object term URI is not a URI ref. Next, in order to create sequences, we have used the BFS function in order to find all the paths in such a sequence. The generate sequences function calls this BFS function to generate all the possible sequences for all the entities as starting point in the graph. The max depth tells the graph tells what should be the depth to which the BFS search would continue. We have taken all the inputs from the triples files and converted into the graph, and from which we have fixed the max depth to be 5 and extracted sequences from them. As we can see, the total number of entities in the graph with whom there is no literal connection is 44,740. There are 22 distinct relations, and by doing BFS, we have found approximately 63 lakhs paths. We have also displayed a random path to show how it looks like. As we can see from the links, there are alternate nodes, and in between two nodes, there are relations. Next, we have fed the sequence to the what to bake model. Here, we have told the model that we want embeddings of size 100, and we have made the context window to be of length 5. Also, we have set the mean count value to 1, meaning that all the nodes are considered. But after we have embedded, we can see that we have all the entities embedded. We have just checked that which of the nodes other than entities have been also embedded. We can check that these are most of the relations for which we have obtained embedding successfully. We also take one of the random entities from our dataset and check the size of the size and data type of the embedding. As we have seen here, we have the entity which is an art material class, and we have corresponding entity present here.
Hello everyone, I am Dhanush. Now I want to start about embedding comparisons. The quality of embeddings can be evaluated by noting that embedding of related concepts must be closer together, and embeddings of unrelated concepts must be far apart. Using this idea, we can check the quality of embeddings by performing a link prediction test using any fixed model. A link prediction test would take in the embeddings of two nodes and predict the existence or non-existence of a linking relation between them. We expect better embeddings to give a greater accuracy on this task, irrespective of the model used to make the actual prediction. Let's dive into the code part. So we are using a deep learning model with one FC layer followed by a sigmoid layer. It takes both head and tail embeddings and output a probability of link between them. For the going to the training and evaluation part, first we are concatenating both head and tail embeddings and pass it to the classifier model. We are using BC loss, that is binary cross entropy loss, and Adam optimizer for training. Dataset is divided into train and validation, and we are evaluating the performance of the model by validation accuracy. Let's look at the results. We observed that the random embeddings the best validation accuracy is 72.6%, and while for that of trans C embeddings is around 70.4. By comparing these two with RDF2 vector embeddings, which is far greater than those two with 92.8% accuracy, we can clearly say that RDF2 vector embeddings are best from the taken random embeddings, trans embeddings, and RDF2 vector embeddings. Thank you.